For thousands of years, the Milky Way has been a glowing river of light in our night sky, familiar yet deeply mysterious. In 2025, with new maps, sharper telescopes, and better simulations than ever before, astronomers are finally beginning to trace the true structure of our galactic home, its sprawling spiral arms, crowded core, and dark matter halo. Tonight we journey through the Milky Way itself, from the quiet suburbs where our sun lives to the turbulent heart of the galaxy. If you enjoy voyages like this, please like, subscribe and share, and tell us in the comments which region of the Milky Way would you most want to see up close. Thank you for watching. Now let's begin. The journey through the Milky Way begins outside the galaxy, with the environment that surrounds it on the scale of many millions of light years. The Milky Way is part of a gravitationally bound collection of galaxies called the local group. A galaxy group is a small association of galaxies whose mutual gravity keeps them together against the general expansion of the universe. In this case, the local group fills a region roughly 10 million light-years across, and contains on the order of several dozen to about 50 known galaxies, with more very faint members still being identified as observations improve. Two large spiral galaxies dominate the luminosity and mass of this system, the Milky Way and the Andromeda Galaxy. A third spiral, the Triangulum Galaxy, is smaller but still contributes non-negligible mass and light. The remaining members are mostly dwarf galaxies of different types, including irregular dwarfs and dwarf spheroidal systems which orbit the larger spirals or move through the common gravitational potential of the group on extended paths. From the observed motions of these galaxies, and from models of how gravity slows the local expansion, astronomers infer that the total mass of the local group is several trillion times the mass of the Sun, much larger than the mass that can be accounted for by stars and gas alone. The local group sits inside a still larger structure known as the local sheet. A galaxy sheet is a flattened arrangement in which galaxies share similar motions and lie near a common geometrical plane. In this region, the local group and neighbouring groups of galaxies move together with only small differences in velocity, indicating that they are embedded in a coherent structure tens of millions of light-years in extent. Beyond the local sheet, the pattern of galaxy motions changes noticeably, marking the transition to other structures and to a neighbouring low-density region called the local void. On even larger scales, the local group occupies a position near the outer parts of a vast concentration of matter, often referred to as the Laniakea supercluster, a region where many groups and clusters of galaxies follow related flow patterns shaped by surrounding overdensities and voids. This supercluster is not a single bound object, but part of the network of filament sheets and underdense regions that together form the large-scale structure of the observable universe. Within the local group, the distribution of mass has a roughly dumbbell-like character. One main concentration is centered on the Milky Way and its satellites, and the other is centered on Andromeda and its own satellites. The combined center of mass, or barycenter, lies in the space between these two spirals. Both galaxies move within the group potential and also move relative to each other. Measurements of Andromeda's motion across the sky and along the line of sight show that it is currently approaching the Milky Way at a speed of a little more than 100 kilometers per second, a value derived from the Doppler shift of its light and from precise astrometric data. This approach speed reflects their mutual gravitational attraction and the mass of their extended dark matter halos. The detailed future orbit and possible eventual merger of the two galaxies depend on factors such as their transverse velocities and the distribution of mass in the group, and are topics of continuing research. But for the present description, it is sufficient to note that they define the two dominant mass centers of the local group. Around each of these spirals there is a system of satellite galaxies. The positions and motions of these satellites provide important constraints on the underlying mass distribution, because their orbits respond to the combined gravity of visible matter and dark matter. Dark matter is a form of matter that does not emit, absorb, or reflect light, but exerts gravitational influence. In galaxy groups like the local group, dark matter accounts for most of the total mass. Evidence for this comes from the speeds of galaxies within the group, from the internal kinematics of its largest members, and from the transition between bound motions inside the group and the more nearly uniform expansion of the universe outside. The space between the galaxies of the local group is filled by the intergalactic medium. The intergalactic medium is a very diffuse mixture of mainly ionized hydrogen and helium, together with small amounts of heavier elements. In the local group, this gas has extremely low density compared with a gas in galaxies, yet it contains a substantial fraction of the ordinary or baryonic matter present in the region. Its temperature and ionization state are set by a balance between heating from ultraviolet and X-ray background radiation shocks from structure formation and cooling processes such as radiative emission. Because the gas is so tenuous, it does not usually appear as a bright glowing component. Instead, it is studied through its absorption signatures in the spectra of distant background sources such as quasars, through its influence on the extended gaseous halos of galaxies, and through numerical simulations that follow the growth of structure. The local group itself occupies a region where the gravitational pull of its mass is strong enough to slow and locally overcome the general Hubble expansion. Just beyond this region, galaxy velocities line up with a relatively smooth outward flow, sometimes described as a cold Hubble flow, because of the small scatter around the average relation between distance and recessional velocity. The change from bound motions inside the group to this smoother flow outside marks a practical boundary for the gravitational influence of the local group. Inside that boundary, galaxies remain members of the group and interact over cosmological timescales. Outside it, they participate more fully in the large-scale expansion and in the dynamics of neighbouring groups and filaments. At this outermost stage of the journey, the Milky Way is therefore treated as one component of a small galaxy group embedded in a sheet of galaxies which in turn lies within the broader cosmic web. What matters here are its mass, its role as one of the two dominant spirals of the local group, and its position with respect to Andromeda Triangulum and the surrounding dwarf galaxies. The detailed internal structure of the Milky Way, including its halo disk and central regions, remains unresolved at this scale. The Milky Way is not isolated but surrounded by a population of smaller satellite galaxies, and by extended structures of stars that trace past gravitational interactions. A satellite galaxy is a much less massive system that remains gravitationally bound to a larger galaxy and orbits within its dark matter halo. Around the Milky Way, astronomers have confirmed several dozen such satellites within a few 100,000 light-years, and surveys continue to reveal new faint members that add to this census. Catalogues compiled from recent observations list more than 60 small galaxies within a few 100,000 parsecs of the galactic centre, although not all are certainly bound, and theoretical models predict that many more satellites of very low luminosity are likely to exist but remain undetected. The most prominent satellites visible in the night sky from Earth's southern hemisphere are the Large Magellanic Cloud and the Small Magellanic Cloud. Both are irregular dwarf galaxies with active star formation, significant reservoirs of gas and stellar populations that span a wide range of ages and chemical compositions. Their motions and internal dynamics indicate that they are relatively massive among dwarf galaxies, and may themselves be a bound pair moving together through the outer regions of the Milky Way halo. In addition to the Magellanic Clouds, there are many dwarf spheroidal galaxies with low luminosity and low surface brightness, such as the Sagittarius dwarf spheroidal galaxy sculptor, Fornax Draco, and others. These systems are dominated by dark matter, in the sense that their observed stellar kinematics cannot be explained by the mass in stars alone. Their stars typically have low heavy element abundances, indicating that chemical enrichment in these small systems has been limited by weak gravitational potential wells and by the loss of gas through feedback and environmental effects. Wide-area imaging surveys using instruments on large telescopes have extended this list with ultra-faint dwarf galaxies that contain very small numbers of stars and have extremely low luminosity, but which still appear to be embedded in substantial dark matter halos. Some of the faintest known satellites have only a few dozen identified member stars, and yet show velocity dispersions consistent with total masses hundreds or thousands of times larger than the mass in visible stars. Statistical studies and cosmological simulations suggest that the total number of satellites, including those below, present detection limits may be considerably higher than the number currently known, possibly by factors of order a few. The spatial distribution and orbital properties of these satellites provide important information about the formation and evolution of the Milky Way. In the standard picture of hierarchical structure formation, a large galaxy grows over time by accreting smaller systems whose stars, gas, and dark matter become part of the larger halo and disk. Some satellites survive as recognizable galaxies for long periods, while others are disrupted by tidal forces. Tidal forces arise because gravity from the host galaxy acts more strongly on the near side of a satellite than on the far side, stretching the satellite and gradually removing loosely bound material. As the satellite orbits stripped, stars can form elongated streams that approximately trace its past orbit through the halo. The Sagittarius dwarf spheroidal galaxy provides a clear example of this process. It is currently in an advanced state of disruption, and its stellar debris forms a large tidal stream that wraps around the Milky Way on an orbit that is roughly polar with respect to the galactic disk. Observations of this stream, together with models of its formation, constrain the mass distribution and shape of the Milky Way's dark matter halo, because the stream's path is sensitive to the underlying gravitational potential. Other tidal streams have been identified in the halo using photometric surveys and precise stellar positions, proper motions and velocities, particularly from the Gaia mission. These streams vary in length, width, and stellar content, and some are likely remnants of dwarf galaxies, while others may originate from disrupted globular clusters. Together they form a network of thin structures embedded in the diffuse stellar halo. The Magellanic Clouds have also produced extended gaseous features, including the Magellanic Stream, a long ribbon of neutral and ionized gas that trails behind them and leads ahead of their motion. This stream is thought to arise from tidal and hydrodynamic interactions between the clouds and the Milky Way, although the relative importance of gravitational stripping and ram pressure remains an active area of study. The existence of such features shows that satellite galaxies do not orbit passively, but exchange mass and angular momentum with their environment. In numerical simulations that follow the orbital evolution of the Large Magellanic Cloud, within a realistic Milky Way halo, the mass of the satellite and its motion induce a reflex response in the outer halo of the Milky Way itself, slightly displacing the galactic center of mass and perturbing the orbits of halo stars. High-precision astrometric data now allow these effects to be probed directly by comparing measured stellar motions with model predictions. Current and planned deep surveys, including those that will be carried out by wide-field facilities, with high sensitivity to low surface brightness structures, are expected to increase the known satellite population and reveal additional streams of stars and gas. These discoveries will further refine estimates of the total mass of the Milky Way, the clumpiness of its dark matter halo, and the frequency of past accretion events. By combining observations of satellite galaxies, stellar streams, and associated gaseous structures, astronomers build a detailed view of the recent and ongoing accretion history of the Milky Way and of the role that discrete satellites play in shaping the outer halo. The Milky Way contains far more mass than is visible in its stars' gas and dust, and most of this additional mass is arranged in an extended dark matter halo that surrounds the luminous parts of the galaxy. Evidence for this halo comes from multiple dynamical tracers whose motions respond to the total gravitational potential. One key observable is the galactic rotation curve, which is the variation of circular orbital speed with distance from the galactic center. If the mass of the galaxy were concentrated only where most of the light is, the rotation speed would rise in the inner regions and then decline roughly as the inverse square root of distance. Observations instead show that orbital speeds of gas and stars reach values of a few hundred kilometers per second in the inner tens of thousands of light years, and then remain nearly constant over a large radial range, with recent data indicating a gradual decline only beyond several tens of thousands of light years. A rotation curve of this form requires that the enclosed mass continue to increase roughly, in proportion to radius over much of the disk and inner halo. The distribution of visible matter alone does not provide enough mass at large radii to explain the measured speeds, so an additional, more extended mass component is required. This component is modelled as a dark matter halo because it does not emit or absorb detectable light, but contributes to the gravitational field. Modern studies combine rotation curve measurements with information from stellar halo kinematics, globular clusters, satellite galaxies, and stellar streams to estimate the mass profile of this halo. A mass profile describes how the enclosed mass changes with radius from the galactic center. Different analyses adopt different functional forms of the halo density profile, such as cuspy profiles that rise steeply toward the center, or profiles with a shallower central behavior, and they fit these models to the data under various assumptions about the symmetry of the halo and the motions of tracer populations. Despite differences in detail, there is broad agreement on the overall scale of the Milky Way halo mass. Many recent estimates place the total mass within a radius of order 200,000 to 600,000 light-years, in the range from roughly 600 billion to about 2 trillion times the mass of the Sun. Individual methods such as line of sight, mass estimators applied to satellite galaxies, spherical genes, analyses of halo stars, or fits to the outer rotation curve often quote uncertainties of several tens of %, reflecting both measurement errors and modelling systematics. Discrepancies between methods are common, but most results cluster around a value of about 1 trillion solar masses for the total halo, with some studies finding somewhat lower masses and others somewhat higher. The precise value matters for questions such as the orbits of satellite galaxies and the timing of future interactions with nearby large galaxies. But for the purpose of describing the structure of the Milky Way, it is sufficient to treat the dark matter halo as the dominant mass component beyond the bright stellar disk. The radial extent of the halo is often characterized by a virial radius, which is a conventional boundary within which the average density is a fixed multiple of the critical density of the universe. For the Milky Way, this virial radius is typically estimated to be of order 200,000 to 300,000 light-years. The luminous stellar disk, by comparison, has a radius of order 50,000 light-years, so the dark matter halo extends several times farther than the main disk and encompasses all of the satellite galaxies and stellar streams that orbit in the outer regions. Within the solar radius, the contribution of dark matter to the local mass density has been inferred from the vertical motions of stars near the galactic plane and from detailed models of the rotation curve. These analyses suggest a local dark matter density comparable to a few tenths of a giga electron-volt per cubic centimeter, with quoted uncertainties that reflect the sensitivity to assumptions about the baryonic mass distribution and the details of the halo profile. The overall density profile of the halo is usually described by parametrized models that can be compared with expectations from cosmological simulations. Many studies find that a profile similar to that of halos in cold dark matter simulations provides an adequate description of the Milky Way data. Though recent high-precision measurements of the rotation curve and of stellar halo kinematics indicate possible deviations from simple forms, especially in the innermost and outermost regions. In particular, the rotation curve may decline more strongly beyond several tens of thousands of light-years than in some earlier models, which would reduce estimates of the outer halo density at those radii. The shape of the dark matter halo is another important but challenging property to determine. The simplest assumption is that the halo is spherically symmetric, but this is unlikely to be exact. Observational constraints use the flaring of the gas disk, the motions of halo stars, and the paths of stellar streams such as the Sagittarius stream to infer whether the halo is more nearly spherical, oblate, prolate, or triaxial. Results are not fully consistent, but many analyses favor a halo that is close to spherical or mildly flattened within the inner tens of thousands of light-years, with possible changes in shape at larger radii. More recent work combining Gaia data with models of the accreted stellar halo suggests that the dark matter halo may be triaxial and tilted with respect to the galactic disk, although the level of triaxiality and the orientation remain uncertain. Time-dependent effects, including the influence of massive satellites such as the Large Magellanic Cloud, and the fact that the halo is still assembling material, further complicate the interpretation, because they mean that the halo may not be in a perfectly steady state. In theoretical treatments, the dark matter halo of a galaxy like the Milky Way forms through the gradual aggregation of smaller halos along filaments of the cosmic web, and its present-day structure retains signatures of this growth history in the form of subhalos, anisotropies, and phase space streams. Many of these features are now being probed using precise positions and velocities from large stellar surveys. As a result, the view of the Milky Way halo is shifting from a simple, smooth static background to a complex evolving component whose detailed density, profile, shape, and substructure are still under active study, even though its existence and approximate mass scale are well established. The stellar halo of the Milky Way is a diffuse extended component of stars that surrounds the central regions, the disk and the bulge, reaching to distances of at least many tens of thousands of light-years from the galactic center, and probably beyond 100,000 light-years. Unlike the thin disk, which is dominated by stars on nearly circular co-rotating orbits, confined close to the galactic plane, the stellar halo is characterized by stars on eccentric, often highly inclined orbits that reach large heights above and below the plane. Most halo stars are old and have low abundances of elements heavier than helium, indicating that they formed early in the history of the galaxy, or in low-mass systems where chemical enrichment proceeded slowly. Observationally, the stellar halo is traced by specific types of stars that can be identified at large distances, such as blue, horizontal branch stars, R Lyrae variables, K giant stars, and main sequence turn-off stars selected in deep surveys. Measurements of their positions, velocities, and chemical compositions are combined to build a three-dimensional view of the halo's structure and kinematics. The overall density profile of the stellar halo declines with radius more gradually than a simple exponential disk, but more steeply than a constant density distribution. Analyses based on wide-field surveys have found that a broken power law provides a good description, with an inner slope of roughly 2 to 3 and a steeper outer slope of roughly 4 to 5, and with a break radius around 20 to 30 kiloparsecs from the galactic center. Inside this break radius, the stellar halo is noticeably flattened with an axis ratio significantly less than 1, while farther out it becomes closer to spherical. The total stellar mass in the halo is small compared with the stellar mass of the disk and bulge, amounting to at most a few % of the galaxy's total stellar content. But the halo carries important information about the early stages of assembly and merging. In velocity space, halo stars show large random motions with characteristic speeds of several hundred kilometers per second, and only modest net rotation compared with the disk. Studies using data from the Gaia mission have shown that the inner stellar halo is dominated by stars on highly radial orbits, meaning that their paths carry them to large distances from the galactic center, and then back again with relatively small angular momentum. This population, often associated with a major accretion event sometimes labeled Gaia sausage enceladus, displays distinct chemical abundance patterns and kinematics that suggest it originated in a relatively massive dwarf galaxy that merged with the Milky Way roughly 10 billion years ago. Other structures in the halo, such as retrograde streams and groups of stars with common orbital properties, indicate additional accretion events, including at least one that brought in a significant number of retrograde stars and some globular clusters. These findings support the view that a large fraction of the stellar halo formed through the accretion and disruption of smaller galaxies over time. At the same time, dynamical and chemical analyses suggest that a non-negligible minority of halo stars may have formed in situ within the main progenitor of the Milky Way, and were later moved to halo-like orbits by early mergers or by internal dynamical processes. The spatial and kinematic separation between accreted and in situ populations remains an active area of research, but it is clear that the halo cannot be treated as a single, well-mixed component with uniform properties. Embedded within the stellar halo is the system of globular clusters associated with the Milky Way. A globular cluster is a dense, gravitationally bound system of stars with a roughly spherical shape and typical radii of only a few tens of light years, containing from tens of thousands to several million stars. These clusters are generally old, with typical ages of 10 to 13 billion years, and they provide nearly coeval stellar populations that are valuable for calibrating stellar evolution models and for constraining the age of the galaxy. The Milky Way is known to host more than 150 globular clusters, and recent compilations that combine optical and infrared surveys, improved distance estimates, and revised classifications suggest that the number of confirmed clusters is now close to 170, with some remaining uncertainty, and the possibility that additional clusters are still hidden by dust or confusion in crowded fields. The spatial distribution of globular clusters is strongly concentrated toward the galactic center, with many clusters lying in the halo at distances of several to tens of kiloparsecs, and a significant subset associated with the bulge and inner regions. Some clusters show disk-like kinematics and metallicities, and are associated with the thick disk component, while others follow extended, often eccentric orbits characteristic of the halo. The metallicity distribution of globular clusters is broadly bimodal, with one group of metal-poor clusters sharing properties typical of the stellar halo, and another group of more metal-rich clusters linked to the bulge and thick disk. Detailed studies of individual clusters combining color magnitude diagrams with high-resolution spectroscopy reveal multiple stellar populations with small but significant differences in chemical abundances, especially in light elements such as sodium, oxygen, and aluminium. These abundance patterns are interpreted as evidence for complex early enrichment histories within clusters, although the exact formation mechanisms remain under investigation. The orbits and chemical properties of globular clusters also provide a record of past accretion events. Many clusters can be grouped according to their total orbital energy angular momentum and detailed abundance patterns into families that are associated with specific merger events or progenitor galaxies. For example, a subset of halo clusters appears to share orbital properties and chemical signatures with the Gaia sausage Enceladus population, while others are linked to different accreted systems identified in phase space. Recent work has proposed classification schemes that distinguish clusters formed in situ in the main Milky Way progenitor from those that formed in external dwarf galaxies and were later accreted. In this picture, metal-rich clusters on relatively low-energy disk-like or bulge-like orbits are more likely to have formed in situ, whereas many metal-poor clusters on high-energy halo-like orbits are more likely to be accreted, although there are exceptions and overlaps. There is also evidence that some massive globular clusters, particularly those with extended stellar envelopes or internal metallicity, spreads larger than typical for clusters may be the stripped nuclear remnants of dwarf galaxies rather than ordinary clusters. Taken together, the stellar halo and the globular cluster system form a combined record of the assembly history of the Milky Way. Their ages, metallicities, spatial distributions, and kinematics encode information about the timing, mass, and orbital characteristics of the galaxies that merged to build the present halo, as well as about the early star formation conditions in the main progenitor. Ongoing and future surveys that provide deeper photometry, more precise astrometry, and large samples of high-quality spectra are expected to refine this picture further, revealing additional substructure in the halo and more subtle patterns in the globular cluster system, while continuing to clarify the balance between accreted and in situ components in the outer regions of the galaxy. The region around the Milky Way contains not only stars and dark matter, but also a large mass of diffuse gas that forms a hot and warm-hot circumgalactic medium. The circumgalactic medium is the gas that occupies the volume within the galaxy's dark matter halo but outside the main stellar disk and bulge. Observations of this medium use absorption and emission lines from highly ionized atoms, especially oxygen, in states that correspond to gas at temperatures of hundreds of thousands to several million degrees. In the Milky Way, detections of absorption by oxygen, 6 in ultraviolet spectra, and oxygen 7 and oxygen 8 in X-ray spectra toward background quasars and active galactic nuclei, demonstrate that there is a widespread reservoir of ionized gas extending to large distances from the galactic plane. Emission from these ions mapped over wide areas of the sky provides complementary information on the temperature and density structure of this gas. Analyses of oxygen 7 and oxygen 8 emission and absorption have shown that the Milky Way hosts a hot gaseous halo with characteristic temperatures of roughly 1 to a few million degrees. The density of this gas decreases with distance from the galactic center and from the galactic plane, but it remains detectable out to at least tens of thousands of light-years and likely to radii comparable with the estimated virial radius of the dark matter halo. Models that fit the distribution of line strengths on different sight lines usually adopt simple radial profiles for the gas density and adjust their parameters until they reproduce the observed column densities and surface brightnesses. These studies typically infer total masses in the hot halo of order several tens of billions of solar masses, with quoted ranges reflecting the choice of density, profile, metallicity, and outer radius. This mass is significant compared with the mass of stars in the galaxy, and indicates that the circumgalactic medium is an important baryon reservoir, although it does not by itself fully account for the difference between the total baryon content expected from cosmological measurements and the amount directly observed in stars and cold gas. In addition to the hot phase traced by highly ionized species, there are cooler and denser components of the circumgalactic medium. These include warm ionized clouds at temperatures of tens to hundreds of thousands of degrees, and cooler neutral clouds with temperatures closer to the classic warm and cold phases of the interstellar medium. Observations of high-velocity clouds, which are gas clouds, moving at speeds of many tens to more than 100 kilometers per second, relative to the local standard of rest, show that such material is present at distances of many thousands of light-years above and below the galactic plane. Distance measurements using absorption against background halo stars have placed many of these clouds firmly within the halo, rather than in the more distant intergalactic medium. Their chemical compositions indicate a mixture of near-solar and subsolar metallicities, implying that some clouds originate in gas that has been processed in the galactic disk and expelled, while others likely carry material that has not yet been strongly enriched. The coexistence of hot diffuse gas and cooler clouds suggests a multi-phase structure in which cool and warm gas moves through and interacts with a hotter background. Theoretical models and numerical simulations support this picture, showing that cool clouds traveling through a hot medium can be ablated, mixed, and sometimes condensed, while feedback from star formation and supernovae can drive hot outflows that later cool and return. Gas flows in the circumgalactic medium therefore include both inflow and outflow. Inflow is supplied by material accreting from the larger scale environment, and by gas that cools from the hot medium and moves back toward the disk. Outflow is driven primarily by stellar feedback in the disk, and to a lesser extent in the Milky Way by past activity of the central black hole. Measurements based on ultraviolet absorption lines toward bright sources indicate that the combined rate of inflow and outflow through the halo is comparable to or larger than the present star formation rate in the disk. This balance suggests that the circumgalactic medium plays a central role in regulating star formation over long timescales by supplying fresh gas and by temporarily storing material expelled from the disk. The interface region between the disk and the halo is the site of a galactic fountain, in which hot gas produced by supernovae rises from the disk, expands and cools in the lower halo, and then falls back after losing energy and mixing with ambient halo gas. Observations of intermediate velocity clouds and of ionized gas layers above the disk support the existence of such a circulation pattern. Simulations indicate that fountain flows can promote the condensation of fresh cool gas from the hot halo, effectively converting some of the circumgalactic medium into infalling clouds that replenish the interstellar medium. At larger radii, where the direct influence of individual supernovae is weaker, the hot halo is closer to hydrostatic balance in the combined gravitational potential of the dark matter halo and the baryonic components. In this regime, the gas density and temperature profiles are set by the competition between gravitational heating during structure formation shock heating by accretion, radiative cooling and heating by the integrated output of stellar populations, and any past outburst from the central region. Different analytic and numerical models explore whether the hot halo is best described by quasi-hydrostatic configurations, cooling flows, precipitation-limited states, or combinations of thermal and non-thermal pressure support. For the Milky Way observations of oxygen line emission and absorption, together with constraints from pulsar and fast radio burst dispersion measures, limit the range of allowed density and temperature profiles, but still leave non-negligible uncertainties, especially at large radii. There is active work comparing these models with X-ray data, ultraviolet absorption measurements, and cosmological simulations of galaxies similar to the Milky Way, with the goal of refining estimates of the total circumgalactic baryon content and clarifying how the halo is partitioned among hot, warm, and cool phases. In this framework, the gaseous halo is not a static atmosphere but an evolving component that exchanges mass, energy, and metals with both the galactic disk and the surrounding intergalactic medium, while its global properties remain constrained by the overall gravitational potential of the Milky Way and by the energy and momentum supplied by feedback processes. Between the extended gaseous halo and the main body of the Milky Way disk lies a transition region, in which gas kinematics, temperature, and phase structure change from halo-like conditions to disk conditions. This region, often called the disk-halo interface, contains extraplanar gas layers, intermediate and high-velocity clouds at known distances of a few to several thousand light-years above the plane, and ionized gas that rotates with the disk but lags in speed with increasing height. Observations of neutral hydrogen in the 21 cm line show that the galactic HV distribution is not confined to a thin layer but extends into an extraplanar component that follows galactic rotation with a modest lag. Studies of the 21 cm emission profile wings near the galactic poles and in directions away from the plane have revealed a population of clouds and filamentary structures that move at velocities close to that expected for disk rotation, yet lie at heights of up to several thousand light-years, indicating that a significant fraction of the neutral gas is located in a thick vertically extended layer. Modelling of this component suggests that roughly 10% of the total HI mass may reside in such extraplanar gas, with a scale height larger than that of the classical cold and warm neutral medium in the thin disk. In addition to the neutral component ultraviolet absorption line, studies reveal ionized gas at intermediate and high velocities in front of halo stars and extragalactic background sources. These features associated with intermediate velocity clouds and high velocity clouds provide direct information on the distances and therefore heights of the absorbing gas above or below the plane. Analyses that combine absorption line velocities with accurate stellar distances show that many intermediate velocity clouds lie within a few thousand to roughly 10,000 light-years of the disk, placing them firmly in the disk-halo interface rather than in the more distant circumgalactic medium. Their metallicities are often near solar or mildly subsolar, suggesting that a substantial fraction of this material originates in the galactic disk and has been transported upward, although some clouds have lower metallicities consistent with a mixture that includes accreted halo or satellite material. The kinematics of these clouds and of the ionized gas layers point to a circulation pattern commonly described as a galactic fountain. In this picture, gas is heated and accelerated by supernova explosions and stellar winds. In the disk rises to heights of a few thousand light-years, interacts with the surrounding halo gas, cools, and eventually falls back toward the plane. Hydrodynamic simulations of such fountains show that cool or warm clouds ejected from the disk can be ablated and mixed with the hot halo medium, but that under realistic conditions a significant fraction of the cool gas can survive for several 100 million years, especially for clouds larger than a few hundred parsecs in radius. During their trajectories, these clouds can entrain ambient halo gas, increasing their mass and altering their chemical composition. As they cool and condense, they contribute to the inflow of fresh gas back onto the disk, thereby linking feedback-driven outflows to subsequent gas accretion. Observationally, signatures consistent with fountain flows include vertical gradients in rotation speed with extraplanar gas lagging behind the thin disk inflow components detected in emission and absorption toward the inner galaxy, and correlations between regions of strong star formation in the disk and features in the overlying halo gas. In external edge on galaxy studies of extraplanar Hi and H, alpha-emitting gas show inflow velocities of tens of kilometers per second toward the disk and scale heights of several thousand light-years, supporting the idea that fountain-driven circulation and halo accretion are common phenomena in galaxies like the Milky Way. The disk-halo interface is also the region where cold or cool gas accreting from the circumgalactic medium first encounters the structured magnetized interstellar medium of the disk, high-velocity clouds that are located at distances of tens of thousands of light-years and are on trajectories that intersect the disk will eventually enter this interface zone. As they do so, their velocities relative to the rotating disk gas decrease through interaction and drag, and they fragment into smaller clumps embedded in a more diffuse envelope. Some high-velocity complexes, including well-studied features at large galactic longitudes and latitudes, show evidence of this gradual deceleration and fragmentation as they approach the disk. Estimates of the total mass in high-velocity clouds and of their infall timescales suggest that the associated gas accretion rate is of the same order as the present-day star formation rate, although the exact contribution depends on assumptions about cloud distances, ionized fractions, and the fraction of the gas that ultimately reaches the star-forming disk. At lower heights, the transition from halo-dominated conditions to disk conditions also involves changes in turbulence, magnetic field structure, and cosmic ray density. The extraplanar gas exhibits higher velocity dispersions than the cold, neutral medium in the plane, indicating a more turbulent state. Magnetic fields inferred from polarization measurements and Faraday rotation are thought to thread both disk and halo, providing additional support against gravity in the interface region and influencing the morphology of extraplanar filaments and clouds. Cosmic rays produced in supernova remnants diffuse and advect away from the plane, contributing to the pressure balance and potentially helping to drive outflows. The combination of thermal turbulent magnetic and cosmic ray pressures determines the vertical stratification of gas phases and the locations where different components coexist. Chemically, the disk-halo interface contains gas with a range of metallicities, reflecting the mixture of metal-enriched material expelled from the disk and less enriched gas accreted from the halo or from disrupted satellites. Detailed abundance measurements in intermediate velocity clouds show patterns that include both near-solar and significantly sub-solar values, with some evidence that the lowest metallicity components may be linked to gas associated with the outer halo or to debris from satellite galaxies. This diversity in metallicity, together with kinematic and spatial information, allows researchers to separate different origins and to estimate the relative importance of recycled versus newly accreted gas in feeding the disk. Overall, the disk-halo interface is a vertically extended multiphase region in which extraplanar neutral and ionized gas rotates more slowly than the midplane, where clouds and filaments trace both upward motion, driven by stellar feedback, and downward motion associated with cooling and accretion, and where the exchange of mass metals and energy between the galactic disk and the circumgalactic medium is concentrated. The outer disk of the Milky Way is the region where the stellar and gaseous components of the galactic disk extend to large radii where surface densities are low, and where the disk departs most strongly from a flat, thin configuration. Observations indicate that the stellar disk with relatively young populations and the cold gas disk both reach to distances of at least 50,000 to 60,000 light-years from the galactic center, with lower density stellar populations and neutral hydrogen traced even farther out. In this radial range beyond the radius of the Sun, and approaching the edge of the main stellar disk, the disk is warped and flared. A warp is a systematic bending of the midplane away from the inner disk plane as a function of azimuth and radius. In the Milky Way, the warp has been known for decades from maps of neutral hydrogen emission, which show that the HI layer rises above the formal midplane in one galactic quadrant and falls below it in the opposite quadrant at large radii. Quantitative models that fit the vertical displacement of the HI layer as a function of radius find amplitudes of several thousand light-years at galactocentric distances of several tens of thousands of light-years, with the warp becoming more pronounced beyond the radius where the gas surface density has already declined substantially. More recent analyses using red clump stars giants and other stellar tracers show that the warp is not confined to the gas. It is also present in the old stellar disk, indicating that it is a global distortion of the disk rather than a feature of only one component. The detailed shape of the warp, including whether it is symmetric or asymmetric between the two sides of the galaxy, and how its line of nodes is oriented, is still under active investigation, but there is broad agreement that the outer disk is significantly tilted with respect to the inner disk plane, in addition to warping the disk flares at large radii. A flare is an increase in the vertical thickness of a disk component with radius. For the Milky Way, measurements of the HI layer show that the scale height of the neutral gas increases from a few hundred light-years near the Sun to several thousand light-years in the outer disk. Stellar populations also show evidence of flaring. Counts of red clump and giant stars at different latitudes and longitudes reveal that the vertical extent of the stellar disk increases with galactocentric radius, particularly for older populations. This flaring implies that stars and gas in the outer disk occupy a thicker region than in the inner disk, and that the vertical gravitational restoring force is weaker at large radii because the local surface density of matter is lower. Radially, the outer disk is characterized by a steep decline in stellar surface density beyond a break radius. Studies that combine star count spectroscopic surveys and modeling of the integrated light suggest that the surface density profile of the Milky Way disk can be described by an inner exponential with one scale length inside a certain radius and a steeper exponential beyond that radius. The change in slope, often called a truncation or break, occurs at a galactocentric distance of order 40,000 to 50,000 light-years for the main stellar populations, although the exact radius and sharpness of the break depend on the tracer used and on assumptions about the contribution of different disk components. Beyond this break, the stellar density decreases rapidly, but disk stars have been detected at still larger radii, in some cases beyond 70,000 light-years from the center. These detections show that the disk does not end abruptly, but transitions into a regime where disk stars become increasingly rare compared with halo stars, and where their identification requires careful kinematic and chemical separation. The neutral gas disk extends even farther, with HI emission mapped to radii that may approach or exceed 100,000 light-years, though with very low column densities in the outermost regions. Star formation is present, but sparse in the outer disk. Ultraviolet and H-alpha observations of the Milky Way and of external galaxies of similar type show that star formation can occur at gas surface densities lower than those typical of the inner disk, but with reduced efficiency. In the Milky Way, young stellar objects, H2 regions and molecular clouds are observed in the outer disk, although they are less frequent than nearer the center. The presence of young stars at large radii indicates that at least some gas in the outer disk is cold and dense enough to collapse and form stars. At the same time, the outer disk contains older populations whose current locations may reflect radial migration, in which stars born at smaller radii move outward over time because of resonant interactions with spiral arms and the galactic bar. Chemical abundance measurements in the outer disk show that metallicities decline with radius. The radial metallicity gradient defined as the change in heavy element abundance with galactocentric radius is typically negative in the main disk, meaning that outer disk stars and gas are more metal poor on average than inner disk counterparts. Studies using open clusters, Cepheid variables, H2 regions and field stars consistently find a gradient in which metallicity decreases with increasing radius, with indications that the gradient may flatten or change slope beyond the solar radius, and again in the far outer disk. Some open cluster samples suggest that beyond a certain radius, the gradient becomes shallower or nearly constant, possibly reflecting a regime where radial mixing and accretion of lower metallicity gas have modified the simple inside-out enrichment pattern. These abundance patterns provide constraints on models of disk formation, gas accretion, and radial migration, but the outermost gradient and its time evolution remain topics of ongoing study. Kinematically, stars in the outer disk are on nearly circular or mildly eccentric orbits that follow the general rotation of the galaxy, with orbital speeds similar to or slightly lower than those at the solar radius. Measurements of line-of-sight velocities and proper motions for large samples of disk stars show that the rotation curve remains relatively flat out to at least 30,000 to 40,000 light-years, and then may decline gradually at larger radii. In the warped and flared outer disk, however, the vertical motions of stars and gas deviate from simple axisymmetric models. Analyses of three-dimensional velocity fields from modern astrometric surveys have revealed bending and breathing modes in the stellar disk, meaning coherent vertical oscillations of stars above and below the midplane that vary with radius and azimuth. In the outer disk, these patterns appear as wave-like structures superimposed on the warp and flare, indicating that the outer disk is dynamically perturbed. Possible sources of these perturbations include interactions with satellite galaxies such as the Sagittarius dwarf galaxy or the Large Magellanic Cloud misalignments between the angular momentum of the disk and that of the dark matter halo, and internal modes associated with spiral structure. Current models can reproduce some aspects of the observed warp and vertical oscillations, but the relative importance of different mechanisms and the detailed time evolution remain uncertain. The outer warped and flared disk thus represents a region where the Milky Way's disk structure, star formation, chemical gradients, and dynamical state differ significantly from the conditions closer to the center, and where ongoing observations continue to refine estimates of the disk's true size, thickness, and degree of distortion. The outer spiral structure of the Milky Way is traced primarily by gas and young stars in the low-density regions of the outer disk, beyond the solar radius, where the warp and flare described previously are already significant. Spiral arms in a disk galaxy are large-scale patterns in the distribution of gas-young stars and star-forming regions, and in the Milky Way they are identified by combining measurements of distances and velocities for traces such as H2 regions, giant molecular clouds, and massa sources in massive star-forming complexes. Because the Sun lies inside the disk, mapping the outer spiral pattern requires converting observed longitudes, latitudes, and line-of-sight velocities into galactocentric positions using a model for the galactic rotation curve and linking these positions across the sky into coherent arm segments. Radio observations of hydrogen in the 21 centimeter line and of carbon monoxide emission from molecular clouds, together with parallax measurements of masses using very long baseline interferometry, provide the main data sets for this task. Analyses using these tracers show that outside the solar radius, The Milky Way disk contains at least two prominent spiral features, the Perseus arm and the outer arm. The Perseus arm is a major spiral arm located just outside the solar circle with a galactocentric radius of roughly 10 to 11 kiloparsecs. It is identified as an overdensity of molecular gas, H2 regions, and massive star-forming complexes seen in carbon monoxide surveys and in catalogues of radio recombination line sources. Parallax distances to masses in high-mass star-forming regions along the Perseus arm confirm its location and pitch angle, which is the angle between the arm and a circle around the galactic centre. The arm extends around a large fraction of the galaxy in azimuth, although coverage is incomplete in some longitude ranges because of observational limitations, and because distances on the far side of the galaxy are more difficult to measure accurately. The outer arm lies at still larger radii with galactocentric distances that reach roughly 13 to 15 kiloparsecs in many models, and in some directions possibly more. It is traced by molecular clouds and H2 regions with lower surface densities than in inner arms, and by red clump stars in recent photometric studies that map stellar density enhancements in the outer disk. New molecular gas maps from large surveys of the northern outer galaxy show that the Perseus and outer arms appear as quasi-continuous structures in the distribution of molecular clouds with lengths of tens of kiloparsecs. These maps reveal three main spiral segments in the northern outer disk, with the Perseus and outer arms standing out against a more diffuse background of gas. The outer arm is sometimes described as part of an outer pseudo-ring, in which spiral segments at large radii connect to form a partial ring-like pattern when viewed in the plane of the disk. The surface density of gas and the rate of massive star formation in the outer arms are lower than in the inner disk, but they are not negligible. Surveys of massive young stellar objects and compact H2 regions show that high mass star formation occurs along both the Perseus and outer arms, although the number of sites per unit length is smaller than in the inner Scutum Centaurus and Sagittarius Carina arms. This distribution is consistent with a decrease in gas surface density and a lower average pressure in the outer disk, which both tend to reduce star formation efficiency. At the same time, the existence of massive star-forming regions at these radii demonstrates that molecular gas clouds in the outer arms can still reach the densities required for gravitational collapse. In many studies, spiral arms traced by gas and young stars in the outer disk are compared with arms traced by older stellar populations. Infrared surveys sensitive to red giant stars show that the Milky Way appears to have two dominant stellar arms, the Perseus arm and the Scutum Centaurus arm, while the other arms, including the Sagittarius Carina arm and the local arm, are much weaker in old stars and are more prominent in gas and young objects. In this picture, the Perseus arm is a major feature in both gas and stars, whereas the outer arm is more clearly defined by gas and young stars, and may contain fewer old stars relative to inner arms. The exact classification of arms as major or minor depends on the tracer population and on the adopted model, and there is not yet full consensus on the number and relative strengths of arms in the outer disk. The local arm, sometimes called the Orion Cygnus arm, is a smaller segment or spur located between the Sagittarius Carina and Perseus arms, and it contains the Sun and its surrounding star-forming regions. Its status as a true arm or as a spur linked to one of the major arms remains under discussion, with some models treating it as a branch of the Perseus arm and others as an independent segment. In the far outer disk beyond the outer arm, additional structures appear in star counts and gas distributions. One prominent feature is the monochorous structure, or monoceros ring, an overdensity of stars and gas at large radii and low latitudes. There has been debate over whether this structure represents tidal debris from a disrupted dwarf galaxy, or is instead an effect of the flared and warped outer disk, which can produce apparent stellar excesses in certain lines of sight. Recent analyses that model the warp and flare in detail and compare with the spatial distribution and kinematics of stars favor the interpretation that much of the monoceros structure can be explained by the geometry of the warped thick disk, rather than requiring a separate ring. Under this interpretation, the apparent ring is an observational projection of the flared warped outer disk, seen in specific ranges of longitude and latitude. The pattern, speed, and nature of the outer spiral arms are also subjects of current research. Some models propose that the Milky Way hosts two distinct spiral patterns, with an inner pattern associated with certain arms and a slower outer pattern associated with the Perseus and outer arms. In such models, the outer arms may form a pseudo-ring where they nearly close upon themselves round the galaxy. Numerical simulations of disk dynamics show that multiple pattern speeds can arise in barred spiral galaxies, and that outer arms can be produced by resonances with the bar or by interactions with satellite galaxies. Observational evidence for multiple pattern speeds comes, for example, from the differing locations of resonances inferred for the bar and for spiral features but uncertainties in distances, velocities, and the time dependence of patterns limit how precisely these models can be tested. Overall, the outer spiral structure of the Milky Way consists of low but non-zero density arms, principally the Perseus and outer arms traced by molecular gas H2 regions, masers and young stars in a warped flared outer disk. These arms represent the large-scale organization of gas and recent star formation at radii beyond the solar circle, while the detailed number of arms, their continuity, their stellar content, and their exact pattern speeds remain active topics of observation and modeling. In the main disk of the Milky Way, the interstellar medium and the young stellar populations are organized into a spiral pattern that consists of several arms and the lower density interarm regions between them. Outside the region where the bar dominates the global structure of the disk is usually described in terms of four primary spiral arms traced by gas and young stars: the Scutum Centaurus arm, the Carina Sagittarius arm, the Norma arm, and the Perseus arm. Infrared maps that are sensitive to old red giant stars show, however, that only two of these, the Perseus arm and the Scutum Centaurus arm, stand out as major stellar arms with clear overdensities of old stars, while the others, including the Sagittarius and local arms, appear more clearly in gas and young stellar traces than in the old stellar component. This difference highlights that spiral structure can depend on the tracer population. In gas and young stars, the Milky Way exhibits a four-arm pattern, while in older stars the pattern is closer to two main arms linked to the bar. The spiral arms are identified by combining radio observations of neutral hydrogen and molecular gas with catalogues of H2 regions, giant molecular clouds and maser sources in high mass star-forming regions. Distances to masers measured by very long baseline interferometry provide accurate geometric positions for selected points in the arms, and these are used to fix the locations and pitch angles of the arms in models of the galactic spiral pattern. A pitch angle describes how tightly an arm winds around the galactic center, with small angles corresponding to tightly wound arms and larger angles to more open patterns. Estimates of pitch angles for the Milky Way arms span a broad range from values of order 10 degrees to values of order 20 degrees depending on the arm and the method used. In many models, the Scutum Centaurus and Perseus arms emerge as long continuous features with relatively well-constrained geometries, while the other arms and segments are shorter, more irregular or more sensitive to modelling choices. The Scutum Centaurus arm is prominent in the inner and intermediate disk, where it is traced by strong concentrations of molecular gas and massive star-forming regions. The Perseus arm lies outside the solar radius and is a major feature in both gas and stars. The Carina Sagittarius and Norma arms are more pronounced in gas than in old stars, and may function as secondary arms or major gas streams, with less associated stellar overdensity. Between the arms lie the interarm regions, where the surface density of molecular gas and the number density of massive star-forming regions are lower on average than in the arms. A spiral arm in the Milky Way is not a static collection of the same stars, but a region where the density of gas and young stars is enhanced, compared with the background disk. In classical density wave models, spiral arms are long-lived perturbations in the gravitational potential that rotate at a fixed pattern speed different from the local angular rotation speed of the gas and stars. Gas flows into the potential minima associated with the arms is compressed, and forms molecular clouds and stars. In alternative models, spiral arms are more transient recurrent features that arise from gravitational instabilities and swing amplification in the disk evolving on timescales of a few rotation periods. Observations of the Milky Way do not uniquely distinguish between these possibilities, but do provide constraints on pattern speeds and on the relationship between arms and star formation. Measurements based on the kinematics of young stars, open clusters and gas flows suggest that the pattern speed of the spiral arms is lower than that of the bar, implying that the bar and arms are dynamically distinct components. In several studies, the ratio of bar to arm pattern speeds falls between about 2:1 and 3:1, meaning that the bar completes 2 or 3 rotations in the time it takes the spiral pattern to complete one. The location of the corrotation radius of the spiral pattern, where the orbital angular speed of stars equals the pattern speed, remains uncertain, but is generally placed near or outside the solar radius for many models. Within the arms, gas is organized into giant molecular clouds and complexes of clouds. A giant molecular cloud is a cold, dense region of predominantly molecular hydrogen, with typical masses of tens of thousands to several millions of solar masses and sizes of tens of light years. These clouds host the bulk of ongoing star formation in the disk. Surveys of molecular clouds in the inner and outer galaxy show that clouds in spiral arms can be more massive on average than those in interarm regions, and that the surface density of molecular gas is higher in arms. The star formation rate per unit area tends to be higher in arms than in interarm regions because of this enhanced gas density. When star formation rates are normalized by molecular gas mass, however, the differences between arm and interarm regions are often modest. Several studies find that the star formation efficiency, defined as the star formation rate per unit, molecular gas mass, does not vary strongly between arms and interarm regions in the Milky Way or in nearby external galaxies. This result suggests that spiral arms mainly act to gather and organize gas into higher surface densities rather than to change fundamentally the local efficiency with which molecular gas forms stars. Interarm regions contain molecular clouds as well, but they are fewer and often less massive. The interarm gas includes both atomic and molecular phases, and in many models clouds drift out of arms into interarm space as they orbit the galaxy. As clouds leave an arm, they may continue forming stars for a while, before being dispersed by stellar feedback, leading to age gradients in young stellar populations relative to the gas arm. The degree to which such gradients are observed depends on the tracer, the arm and the region studied. In external galaxies, offsets between dust lanes, H2 regions and older stellar bands have been used to test density wave predictions. In the Milky Way, the internal vantage point makes such offsets harder to measure over large scales, but limited evidence from some arms suggests spatial shifts between different traces that are consistent with gas entering, flowing through, and exiting a spiral arm. The vertical structure of spiral arms shows that they are not confined strictly to the midplane. In the warped and flared outer disk, arms follow the warp and flare and can be traced at heights of hundreds to thousands of light-years above or below the nominal midplane. Vertical motions associated with spiral structure, including bending and breathing modes, appear in the full three-dimensional velocity field of disk stars derived from astrometric surveys. Some theoretical models predict that spiral arms can induce coherent vertical motions, and recent analyses of stellar velocity patterns find signatures that may be related to the influence of spiral structure combined with perturbations from satellite galaxies and the bar. Chemically, stars associated with the main spiral arms cover a range of metallicities that reflect both radial gradients and mixing processes. The inner arms tend to contain more metal-rich gas and stars on average than the outer arms, in line with the global metallicity gradient of the disk. Radial migration driven by spiral arms and by the combined action of arms and bar can move stars across significant radial ranges without strongly heating their orbits, altering the local metallicity distribution at a given radius. Evidence for such migration appears in the wide range of metallicities and ages found among stars in the solar neighbourhood, which cannot be explained solely by local chemical evolution. In this context, spiral arms influence not only the spatial distribution of gas and young stars, but also the long-term redistribution of stellar populations across the disk. Interarm regions, being lower density environments, are less prominent in traces of current star formation, but host many intermediate age and old stars that have drifted away from arms over time, or were born during earlier passages. Overall, the main spiral arms of the Milky Way are large-scale rotating patterns in the disk that concentrate gas and recent star formation into curved bands, while the interarm regions contain lower densities of gas and young stars but substantial populations of older stars. The detailed number continuity and strengths of the arms, as well as the exact nature and lifetime of the spiral pattern, remain under active study using radio-infrared and astrometric data, combined with numerical models of disk dynamics. The Sun and its surrounding stellar environment lie within a specific segment of the Milky Way spiral pattern known as the local arm, or Orion arm, which is also called the Orion Cygnus arm or Orion spur in the literature. This structure is a band of stars, gas and star-forming regions located between the larger Sagittarius Carina arm on the inside and the Perseus arm on the outside. Earlier models treated the local arm as a short spur but very long baseline interferometry measurements of trigonometric parallaxes and proper motions for masses in high-mass star-forming regions now show that it extends for tens of thousands of light-years, with a pitch angle comparable to that of the galaxy's major arms, and an active population of star-forming complexes. Estimates based on these massa data and on star counts indicate that the local arm is roughly several thousand light-years wide, and on the order of 20,000 light-years or more in length, placing it in the category of a substantial arm segment, rather than a minor irregular spur. The Sun is situated close to the inner edge of this arm, in a region where the local arm approaches the Sagittarius Carina arm sector on the side nearer the galactic center. Measurements of the distance from the Sun to the galactic center using a combination of stellar orbits around Sagittarius, A-star maser parallaxes, and modeling of the galactic rotation curve converge on values around 8,000 to a little more than 8,000 in units of parsecs converted to light years as roughly 25,000 to nearly 30,000 light years, with quoted uncertainties of a few percent. Within this range, many studies adopt a characteristic distance of about 27,000 light years for descriptive purposes. At this radius, the local arm lies between the inner and outer major arms, and the Sun occupies a position roughly halfway along the known length of the local arm rather than at one of its ends. The local arm contains several well-known star-forming regions and stellar associations, including the Orion complex Cygnus X and other high-mass star-forming regions identified in radio and infrared surveys. These regions host massive molecular clouds, clusters of young stars and H2 regions, ionized by recently formed massive stars. Accurate parallaxes for masses in these complexes place them at distances of roughly 1 to several thousand light-years from the Sun and map their distribution along the arm. The Orion complex, for example, lies at a distance of a few hundred to about 1,000 light-years, while more distant regions in Cygnus and other constellations lie at several thousand light-years. Together they outline a segment of the local arm that passes near the Sun and extends across a substantial range in galactic longitude. The surface density of gas and young stars in the local arm, as inferred from molecular line surveys and from counts of young stellar objects, appears comparable to that in some of the larger arms, supporting the view that the local arm is dynamically significant rather than a marginal feature. Photometric and astrometric surveys in the optical and infrared, most notably those based on Gaia data releases, resolve the three-dimensional distribution of stars within a few thousand parsecs of the Sun, and allow the nearby portion of the local arm to be mapped with increasing precision. These surveys show that the local arm hosts concentrations of young stellar clusters, associations and field stars whose ages span from a few million to several 100 million years, indicating prolonged star formation within this segment. Among the structures identified in these data are complexes such as the Scorpius-Centaurus Association and other groups that trace the recent star formation history of the solar neighborhood. The term solar neighborhood usually refers to the volume of space around the Sun, within which distances, motions, and stellar parameters can be measured with high accuracy, often defined as extending to a few hundred parsecs for detailed kinematic and population studies, and to larger distances for certain types of stars. Within this region, the stellar census is close to complete, down to well-defined magnitude limits, and the three-dimensional velocities of stars can be derived from proper motions, parallaxes, and radial velocities. Analyses of such samples show that the local stellar population is dominated by thin disk stars on nearly circular orbits in the galactic plane, with a mixture of ages from very young to several billion years, and with a metallicity distribution peaked slightly below the solar value and extended toward both lower and higher abundances. A smaller but significant fraction of nearby stars belong to the thick disk, characterized by larger vertical scale heights, higher velocity dispersions, and enhanced abundances of alpha capture elements at a given ion abundance. The separation between thin and thick disk components in the solar neighborhood is statistical rather than absolute, based on combinations of kinematics, chemical abundances, and ages. Kinematically, the motions of stars near the Sun are often described relative to the local standard of rest, which is an idealized circular orbit at the solar radius in an axis-symmetric potential. The Sun's peculiar motion with respect to this standard is determined from the average velocities of nearby stars, and is found to consist of modest components in the radial, tangential, and vertical directions, each of order several to roughly 10 kilometers per second. Velocity dispersions for thin disk stars increase with stellar age, reflecting cumulative dynamical heating. By spiral arms, the bar molecular clouds and external perturbations. Typical dispersions for the oldest thin disk stars in the solar neighborhood reach several tens of kilometers per second, while thick disk stars show still larger dispersions. Modern Gaia-based analyses of samples within a few hundred parsecs reveal that the local velocity distribution is not smooth, but contains multiple overdensities or moving groups such as those associated historically with the Hyades, Pleiades, Sirius, and Hercules streams. These moving groups are ensembles of stars that share similar velocities, but can span a range of ages and chemical properties, indicating that many are not simple dissolving clusters, but dynamical structures produced by resonances with the galactic bar and spiral arms. The presence of these substructures shows that the solar neighborhood is dynamically complex with signatures of both internal disk dynamics and past perturbations. From a structural perspective, the Sun resides within a cavity in the interstellar medium often called the local bubble, surrounded by shells and clouds that are part of the nearby gas distribution. At the level of stellar structure, the key point is that the Sun is embedded in a moderately dense region of the thin disk near the inner edge of the local arm, with immediate surroundings that include a mixture of young associations, open clusters, and field stars, all orbiting the galactic center on paths that reflect the combined influence of the overall disk potential spiral structure and the bar. The solar neighborhood thus provides a representative but dynamically structured sample of thin and thick disk stars within the local arm, offering high-resolution information on the stellar content and kinematics of this specific segment of the Milky Way disk. The local interstellar medium around the Sun is the portion of the galactic gas and dust that occupies the space between stars within a few hundred light-years of the solar system. The interstellar medium is the mixture of gas, dust, and magnetic field that fills the space between stars in a galaxy. In the region surrounding the Sun, this material has low density, is warm and partially ionized, and is arranged into a set of cavities and clouds whose structure is now being mapped in 3 dimensions. The most prominent large-scale feature is the local bubble, sometimes called the local cavity. The local bubble is a cavity of unusually low-density gas, extending for hundreds of light-years in different directions. Estimates based on neutral hydrogen observations and 3-dimensional dust maps indicate that its characteristic extent in the galactic plane is of order several hundred to about 1,000 light-years, though the exact shape is irregular and not well represented by a simple sphere. Within this volume, the average density of neutral hydrogen is only a small fraction of the typical value for the interstellar medium in the Milky Way disk, with representative numbers of roughly 1/10 to 1/5 of the canonical mean density. The local bubble is thought to have been created by the combined action of multiple supernova explosions in nearby stellar associations over the past 10 to 20 million years. These explosions drove hot low-density gas outward, sweeping up ambient interstellar material into an enclosing shell of cooler, denser gas and dust. Modern models and observations suggest that on the sky, the local bubble is elongated along an axis roughly perpendicular to the galactic plane, and is connected to neighboring low-density regions, forming a network of cavities and tunnels rather than a single isolated void. 3-dimensional maps of interstellar dust extinction around the Sun, constructed from large stellar surveys, show that dense gas and dust are organized into a shell and a set of surrounding clouds that trace the boundary of this cavity and separate it from other bubbles in the galactic disk. Within the local bubble, the immediate surroundings of the solar system are often described as the very local interstellar medium. The Sun moves through a flow of low-density, warm, partially ionized gas, whose properties are measured both indirectly through absorption lines in the spectra of nearby stars and directly through in situ detections of interstellar neutral atoms and dust grains that penetrate into the heliosphere. These measurements show that the local gas has temperatures of several thousand Kelvin and densities of hydrogen atoms that are much less than 1 particle per cubic centimeter. The detailed structure of this gas is described in terms of local interstellar clouds. A local interstellar cloud is a small-scale feature of the interstellar medium with characteristic sizes of a few tens of light years, within which the gas has roughly uniform physical properties. The local interstellar cloud, sometimes called the local cloud, is one such region of slightly higher density gas embedded within the local bubble. The solar system either resides within this cloud or near its boundary with another nearby cloud. Current data allow both possibilities because the Sun is close to a transition zone between the local interstellar cloud and the so-called G-cloud. The local interstellar cloud has temperatures of order 7,000 Kelvin and hydrogen densities, estimated at a few tenths of a particle per cubic centimeter, values inferred from absorption line data and from models of how the heliosphere interacts with the surrounding medium. The G-cloud and other nearby clouds, such as the blue cloud and the AQL cloud, are similarly warm, partially ionized structures that share related velocities and physical conditions. Together, they form a cluster of local interstellar clouds with different directions of motion and column densities, whose combined distribution defines the morphology of the local interstellar medium within a few tens of light years of the Sun. Empirical dynamical models based on radial velocity measurements toward nearby stars show that at least several distinct cloud flows intersect the solar neighborhood with relative velocities of a few tens of kilometers per second. These motions and the spatial boundaries inferred from absorption line strengths imply that the local clouds interact with one another and with the larger scale structure of the local bubble shell. The local bubble itself is outlined by denser interstellar material that appears as a shell or wall in three-dimensional dust maps. This shell contains many of the nearest molecular and atomic clouds and is associated with star-forming regions in what is traditionally called the Gould Belt. The Gould Belt is a ring-like distribution of young stars and molecular clouds inclined with respect to the galactic plane, extending for hundreds of light years around the Sun. Many of the best-studied nearby star-forming complexes such as Taurus Ophiuchus, Lupus Chamaeleon, and Perseus lie at distances of roughly 100 to 500 parsecs and form part of this structure. Surveys with infrared space telescopes and millimeter-wave observatories have mapped these molecular clouds in detail, revealing networks of dense filaments, cores, and embedded young stellar objects that trace the ongoing conversion of molecular gas into stars. The positions of these clouds in three-dimensional dust and gas maps align with the boundaries of the local bubble, indicating that much of the surrounding dense material lies in the shell, swept up by past supernova activity. Star formation in these nearby regions is therefore taking place predominantly in the denser gas collected along the edges of the local bubble, rather than in its low-density interior. The local interstellar medium also includes regions of hot gas detected in soft X-ray emission and ultraviolet absorption, though the exact extent, temperature and emission properties of this hot component remain under active study, because part of the observed soft X-ray background arises from charge exchange between the solar wind and interplanetary or interstellar neutrals. After accounting for this contribution, analyses still support the presence of million-degree gas in parts of the local bubble, consistent with a supernova-heated interior. In addition, magnetic fields permeate the local interstellar medium and influence the shapes of cavities and clouds. Modeling of dust polarization data shows that the galactic magnetic field is distorted around the local bubble, with field lines following the shell and being compressed or bent where the shell interacts with neighboring bubbles. These magnetic structures in turn affect the propagation of cosmic rays and the dynamics of gas along the cavity boundaries. Observationally, the structure of the local interstellar medium is constrained by a combination of methods. High-resolution ultraviolet and optical spectroscopy of nearby stars reveals interstellar absorption lines at different velocities from which column densities, temperatures, ionization fractions, and velocities of individual clouds can be derived. Three-dimensional dust maps are constructed by measuring the reddening of stars with known distances across the sky, and inverting these data to obtain the spatial distribution of dust density. X-ray and extreme ultraviolet missions measure emission from hot gas within and around the local bubble. In situ measurements from spacecraft provide direct samples of interstellar atoms, ions and dust grains entering the heliosphere. Combining these datasets yields a picture in which the Sun resides inside a low-density cavity bounded by denser gas and dust, and within that cavity moves through a warm, partially ionized local interstellar cloud complex, whose detailed morphology and dynamics continue to be refined as new observations accumulate. The inner disk of the Milky Way is the region of the stellar and gaseous disk inside the solar radius, where surface densities of stars and gas are highest, where orbital motions remain predominantly circular, but begin to show strong signatures of non-axisymmetric structure, and where the transition toward the central bar and bulge begins in the innermost few thousand light-years. In global terms, the stellar disk of the galaxy is often described by a radial surface mass density profile that is close to exponential over a wide range of radii, with a characteristic scale length of a few thousand light-years. But recent reconstructions that combine Gaia astrometry with large spectroscopic surveys show that this simple picture is incomplete. These studies find that while the outer disk beyond the solar radius follows an exponential decline, the inner disk inside roughly 4 to 5 kiloparsecs has a flatter, nearly constant or slowly varying stellar surface density before rising further into the central regions. This flattened inner component implies that the inner disk contains a substantial fraction of the total stellar mass, and that earlier models which extrapolated the outer, exponential inward, likely overestimated the total stellar mass by a factor of about 2. Vertically, the inner disk consists of at least 2 overlapping stellar components, commonly referred to as the thin disk and thick disk. The thin disk contains most of the young and intermediate age stars and has a small vertical scale height of a few hundred light-years, while the thick disk contains older stars with larger random motions and has a scale height of order 1 to 2,000 light-years. In the inner few tens of thousands of light-years, the midplane stellar density increases toward the center, and the contribution of thick disk stars becomes more important at larger heights, above and below the plane, so that at high distances from the plane, the inner regions are dominated by thick disk populations. Models constrained by star counts and kinematics indicate that the radial scale length of the stellar disk is only weakly dependent on age, whereas the vertical scale height increases strongly with age, consistent with the disk that forms stars in a relatively thin layer and that thickens over time because of dynamical heating and mergers. Within this stellar structure, the distribution and phase balance of interstellar gas in the inner disk show marked radial variations. Atomic hydrogen is present throughout the disk, but inside the solar radius the cold gas becomes increasingly dominated by molecular hydrogen traced by carbon monoxide emission. Kinematic modeling of atomic and molecular gas inside the solar circle, based on large radio surveys, reveals a pronounced ring-like enhancement of molecular gas surface density at galactocentric radii of roughly 4 to 5 kiloparsecs. This feature is often called the molecular ring or galactic ring, and contains a large fraction of the total molecular gas of the disk. Maps of molecular hydrogen column density show this ring as the most prominent structure in a face-on view of the galaxy. The star formation rate surface density follows the molecular gas distribution reasonably closely in the inner disk, with a peak in star formation associated with the molecular ring and a decline toward both smaller and larger radii. In chemical evolution, models reproducing this inner peak in star formation requires including radial gas flows or other dynamical effects associated with non-axis symmetric structures such as the bar, because static models that assume only local evolution tend to underproduce the observed star formation at about 4 kiloparsecs. On smaller spatial scales, star formation in the inner disk proceeds in giant molecular clouds and filaments, whose internal structure and star-forming content are now resolved in extensive surveys. Giant molecular clouds in the inner disk can reach masses of several million times the mass of the Sun, and sizes of many tens of light years. Statistical studies of their star-forming content indicate that the rate at which they form stars correlates strongly with the amount of dense, high-surface density gas, supporting a picture in which the inner disk environment with higher external pressure and higher average gas surface density favors the assembly of large, actively star-forming clouds. The chemical composition of stars and gas in the inner disk reflects both early rapid enrichment and subsequent mixing. Across the main stellar disk, the thin disk exhibits a negative radial metallicity gradient, meaning that average heavy element abundances decrease with increasing radius from the galactic center. Surveys that combine high-resolution spectroscopy with precise distances show that this gradient is steeper for younger thin disk stars and becomes flatter for older populations, while the thick disk displays a mild gradient that can be close to flat or slightly positive. In the inner disk, typical metallicities are higher than in the solar neighborhood, with many stars showing iron abundances above the solar value and enhanced alpha element abundances that record earlier epochs of more intense star formation. These patterns, together with age information, indicate that the inner disk experienced higher star formation rates and more rapid chemical enrichment in its early history than the outer disk, and that radial mixing driven by non-axis symmetric structures has redistributed stars of different ages and metallicities across radii. Kinematically, stars in the inner disk follow nearly circular orbits on average, with orbital speeds of a few hundred kilometers per second, but large datasets from Gaia Data Release 2 and later releases reveal clear departures from simple axis-symmetric rotation. Maps of stellar velocities in the plane show systematic radial and azimuthal streaming motions of order several kilometers per second, which appear as large-scale gradients and wave-like patterns when plotted as functions of radius, azimuth, and height. These patterns are interpreted as signatures of the combined influence of spiral arms and the bar, which drive non-circular motions through resonances and gravitational torques. In particular, negative radial velocity gradients in parts of the inner disk and associated vertical asymmetries indicate that stars respond to non-axis symmetric features that extend over many thousands of light years. The age structure of the inner disk reinforces this dynamical picture. Studies of disk stars with well-determined ages and abundances show that high alpha old stars with substantial orbital angular momentum trace an early phase in which a massive stellar disk was already in place more than 10 billion years ago, and has since survived subsequent merging events, while younger low-alpha stars populate a thinner, more chemically evolved layer. The radial scale length of the disk appears nearly independent of age, suggesting that much of the growth of the disk in radius occurred early, but the vertical scale height increases with age, consistent with the scenario in which the inner disk thickens over time through continued heating and minor accretion. Together, these observational results describe an inner Milky Way disk that is dense in stars and molecular gas, chemically enriched and dynamically complex. the stellar surface density remains high and relatively flat over several thousand light-years inside the solar radius. Before rising toward the very center, the cold gas is concentrated into a strong molecular ring where star formation is particularly active. Metallicity gradients reflect intense early enrichment and subsequent radial mixing, and the velocity field shows clear large-scale streaming motions superposed on overall circular rotation. This central few tens of thousands of light-years of the Milky Way contain a prominent stellar bar that dominates the non-axis symmetric structure of the inner disk and provides the dynamical link between the inner disk and the bulge. In near-infrared light, where dust extinction is reduced star counts, and integrated surface brightness maps show an elongated overdensity, whose major axis is tilted by roughly 20 to a little more than 30 degrees, with respect to the line from the Sun to the galactic center. Analyses that combine extensive red clump giant star counts from all sky, near-infrared surveys, find that this bar has a half-length of about 4.5 to 5 kiloparsecs, so that its full major axis spans of order 9 to 10 kiloparsecs. The bar thickens toward the center and connects continuously to a vertically extended boxy or peanut-shaped bulge, which appears as the three-dimensional inner part of the same bar rather than as a separate component. In this radial range, the bar length orientation and thickness are constrained by fitting the spatial distribution of standard candle stars, and by matching the large-scale gas kinematics leading to consistent pictures in which a single strong bar underlies both the boxy bulge in the inner several thousand light-years and a flatter long bar that reaches outward into the inner disk. The dynamics of stars and gas in the bar region are best described in a reference frame that rotates with the bar at a constant pattern speed. The bar pattern speed is the angular rate at which the bar figure rotates. Hydrodynamical models that reproduce the observed distribution of cold gas velocities, combined with stellar dynamical constraints and resonant features in the velocity distribution of stars near the Sun, indicate that the pattern speed lies in the range of roughly 40 to about 60 kilometers per second per kiloparsec. This places the corrotation radius where stars orbit at the same angular rate as the bar at a galactocentric distance of order 3 to 4 kiloparsecs. Inside corrotation, many stars follow families of stable periodic orbits that in the rotating frame close on themselves and are aligned with the bar. The main such family, often labelled the X1 family in the literature, consists of elongated orbits whose major axes are parallel to the bar major axis, and which provide the backbone of the bar. Closer to the center, near and inside one or more inner Lindblad resonances, set by the combination of the bar pattern speed and the underlying axisymmetric potential, a second family of closed orbits appears. These inner periodic orbits are shorter and oriented roughly perpendicular to the bar major axis, and form the backbone of the innermost more nearly round or lens-like region. Stars at different radii and heights can be trapped around these families, and three-dimensional orbit studies show that vertical resonances and instabilities thicken the bar, leading naturally to a boxy or peanut-shaped bulge as the vertical extension of the same basic bar structure. Gas in the inner disk does not follow these orbits exactly because it is collisional and can shock and dissipate energy. When the gaseous disk responds to the barred gravitational potential, large-scale shocks develop along the leading edges of the bar. In external barred galaxies, these shocks are traced by narrow dust lanes that run nearly straight along the inner edges of the bar. In the Milky Way, modelling of the longitude-velocity distribution of atomic and molecular gas shows that comparable offset dust lanes must be present, although projection effects and extinction complicate a direct image. Hydrodynamical simulations in realistic bar potentials reproduce characteristic features of the observed gas velocity field, such as steep terminal velocity curves and arm-like ridges in emission when the gas flows along X1 like orbits at large. Radii passes through shocks near the bar major axis and loses angular momentum. This loss of angular momentum drives the gas inward, while its energy dissipates so that it settles on progressively more bound orbits that still respect the bar symmetries. At radii of a few kiloparsecs where the corrotation radius and outer resonances lie, the bar drives gas from the inner disk into an inner molecular ring with a radius of about 4 to 5 kiloparsecs, which coincides with the strong molecular ring inferred from carbon monoxide surveys and with the peak in the radial distribution of star formation in the inner disk. Inside this region, further torques and shocks in the bar potential guide some of the gas into narrow lanes that run inward on each side of the bar and feed the central few thousand light years. Within roughly the inner 3 kiloparsecs, gas dynamical models and observations of molecular gas distribution and kinematics indicate that bar-driven inflow continues, and that substantial fraction of the gas is eventually captured onto shorter, nearly perpendicular orbits associated with the inner periodic orbit family. In this inner zone, gas accumulates in a dense rotating structure that forms the central molecular zone, a ring or twisted elliptical feature of molecular gas, extending to a few hundred parsecs from the galactic center. Numerical simulations in which a bar is grown gradually in a galactic disk show that during the growth phase the bar excites strong density waves near the inner Lindblad resonance, which channel gas inward and form a ring associated with these inner orbits. As the system evolves toward a quasi-stationary configuration, the gas in the central molecular zone continues to be supplied along the bar-driven dust lanes, and the ring remains dynamically connected to the larger-scale bar pattern. Inflow rates inferred from observations of gas morphology and kinematics, and from modelling of bar-driven torques, are of order 1 solar mass per year or more, implying that the bar can maintain the mass of the central molecular zone over many orbital periods, even if star formation and feedback remove gas from the region. The stellar bar itself contains a mixture of stellar populations that reflect the secular origin of the structure, chemodynamical analyses that combine large spectroscopic surveys with proper motions and distances find that stars on bar-like orbits exhibit both high alpha metal, rich abundances typical of older thick disk and inner disk populations, and lower alpha, more metal-rich compositions characteristic of the younger thin disk. This mix is consistent with a bar that formed by the dynamical rearrangement of an already existing inner disk, rather than by the direct collapse of a separate component. In such a scenario, stars from different initial radii and heights are trapped into bar-supporting orbits as the bar grows, and then heated vertically during the buckling phase, producing the observed boxy or peanut-shaped bulge. 3-dimensional dynamical models constrained by star counts and kinematics show that the resulting bar and bulge exhibit nearly cylindrical rotation, in which the mean rotation speed depends mainly on distance from the center and only weakly on height above the plane, a pattern confirmed by radial velocity and proper motion surveys of stars in the inner galaxy. Beyond the bar region itself, the gravitational influence of the bar extends well into the surrounding disk and leaves clear imprints on stellar and gas kinematics. In the plane of the disk, the bar corrotation and outer Lindblad resonances give rise to characteristic features in the velocity distribution of stars near the solar radius, including moving groups and streams in the local velocity space that can be reproduced in models with a rotating bar of the measured length and pattern speed. The bar also interacts with the spiral arms, and simulations show that these non-axisymmetric patterns can exchange angular momentum with disk stars and gas, leading to radial migration and further redistribution of angular momentum and metals over time. In this way, the bar plays a central role in shaping orbits and flows throughout the inner few tens of thousands of light-years of the Milky Way, by organizing stellar trajectories into families aligned with the bar, by driving shocks and gas inflow along its leading edges, and by coupling the dynamical evolution of the inner disk to that of the bulge and central molecular gas. The central stellar bulge and the central molecular zone occupy the innermost few thousand light-years of the Milky Way, and represent the densest part of the galaxy in both stars and cold gas, outside the immediate environment of Sagittarius A star. In structural terms, the bulge is not a simple spherical component, but the vertically thick inner part of the galactic bar. Star counts in the near-infrared, where extinction by dust is reduced, show that the bulge has a boxy or peanut-like three-dimensional shape with an X-shaped density distribution when viewed from certain lines of sight. This morphology is revealed by the split in the brightness distribution of red clump giant stars at intermediate galactic latitudes, which indicates that there are two overdensities of stars along the line of sight, corresponding to the near and far arms of an X-shaped structure. Modelling of these star counts shows that the bulge extends roughly 1.5 to 2 kiloparsecs from the galactic centre along the bar major axis, and has a vertical extent of about 1 kiloparsec, with its major axis tilted by about 20 to 30 degrees, with respect to the line from the Sun to the galactic centre. Within this region, the stellar density is high and changes rapidly with position, so that small shifts in longitude or latitude correspond to large changes in the observed surface brightness. The bulge is kinematically distinct from a non-rotating or slowly rotating spheroid. Radial velocity and proper motion surveys of bulge stars show that the mean rotation speed is high and nearly independent of height above the plane. Over a wide range of latitudes, a behavior often described as cylindrical rotation. At the same time, the velocity dispersion is large, with typical values of several tens to more than 100 km per second, depending on position and on the stellar population considered. This combination of strong rotation and high dispersion is characteristic of bar-formed boxy bulges in numerical simulations, and supports the view that the Milky Way bulge is mainly the vertically thickened inner part of the bar, rather than a separate dynamically hot classical bulge that formed in a rapid early collapse. Analyses that fit models to the three-dimensional density and kinematics of bulge stars generally find that any classical bulge component, if present, contributes only a minority of the bulge mass. Estimates vary, but many studies place upper limits of a few tens of % of the total bulge stellar mass for such a component, with several models consistent with no significant classical bulge at all. Chemically, the bulge contains stars spanning a wide range of metallicities. High-resolution spectroscopic surveys reveal at least two broad components: a metal-rich population whose chemical and kinematic properties resemble those of the inner thin disk and bar, and a more metal-poor population with higher velocity dispersion and somewhat different abundance patterns. The metal-rich stars dominate at low galactic latitudes near the plane and show a strong bar-like spatial distribution, while the metal-poor stars become more important at higher latitudes and may include contributions from an early thick disk or from stars accreted in ancient mergers. The mean metallicity decreases with increasing latitude, producing a vertical metallicity gradient across the bulge. Age determinations based on color magnitude diagrams and microlensed dwarf stars indicate that most bulge stars are old, with typical ages greater than about 10 billion years, although there is evidence for younger populations, especially closer to the plane and near the center. These age and abundance patterns are consistent with the scenario in which the inner disk experienced rapid early star formation and enrichment, later developed a bar that buckled to form the boxy bulge, and subsequently continued forming stars in the central regions, while also mixing stars from different radii through bar-driven dynamics. Embedded within this stellar bulge and bar is the central molecular zone, which is the name given to the concentration of molecular gas in the inner few hundred parsecs of the galaxy. In projection on the sky, the central molecular zone extends roughly 1.5 to 2 degrees in galactic longitude on either side of the center, and has a characteristic radial extent of a few hundred parsecs, corresponding to of order 1,000 light-years. Radio and millimeter wave observations of molecular lines such as carbon monoxide and higher density traces show that this region contains a very large mass of molecular gas, with estimates of the total mass ranging from several tens of millions to more than 100 million times the mass of the Sun, depending on the traces and conversion factors used. Although this radial range occupies only a small fraction of the disk, the central molecular zone contains a substantial fraction of the total dense molecular gas in the Milky Way. The gas is organized into giant molecular clouds and complexes with high column densities, strong turbulence, and elevated temperatures compared with typical disk clouds. Line widths of tens of kilometers per second and kinetic temperatures of tens to more than 100 Kelvin are common, indicating a highly dynamic and energetic environment. The spatial distribution of gas in the central molecular zone is not a simple symmetric ring. Position velocity diagrams constructed from molecular line data show coherent streams and arcs of gas with complex kinematics. Many models represent the bulk of the dense gas as lying on one or more elongated rings or streams whose major axes are roughly aligned with the bar minor axis, and whose orbits are associated with the inner family of closed periodic orbits in the barred potential. In these models, gas flows inward along the bar-driven dust lanes, reaches the region near the inner Lindblad resonance, and then settles onto shorter, more circular, or slightly elliptical orbits that form a twisted ring with a characteristic radius of about 100 parsecs. Observed features such as the dense cloud complexes traditionally labeled with Sagittarius designations fit into this picture as segments of one or more gas streams that loop around the center with different line-of-sight velocities. Numerical simulations that follow gas in a realistic Milky Way bar potential reproduce similar patterns when gas loses angular momentum in shocks along the bar and piles up where the dominant orbit family changes from bar-aligned to more nearly perpendicular orbits. Star formation is active but not especially efficient in the central molecular zone. Direct traces of massive star formation, including compact ionized regions, infrared sources associated with young stellar objects, and free radio emission, show that new stars are being born in several of the dense cloud complexes, notably in the very massive cloud near the positive longitude side of the zone and in other prominent regions. However, when the observed star formation rate is compared with the large reservoir of dense molecular gas, the central molecular zone appears to form stars more slowly than would be expected from empirical relations calibrated in the galactic disk and in external galaxies. Quantitative estimates find that the current star formation rate in the central few hundred parsecs is lower by factors of several to about an order of magnitude than predicted by simple scaling with gas surface density. Proposed explanations for this reduced efficiency include the strong tidal field near the galactic center, high turbulent pressures that keep clouds close to but not far beyond gravitational instability, threshold strong shear from differential rotation, and the influence of intense radiation and cosmic ray fields. Observations of dense gas traces combined with measurements of cloud structures and kinematics at high resolution support the idea that many clouds in this region are in an early stage of evolution and may undergo episodic phases of enhanced star formation when conditions allow further collapse. The central molecular zone also participates in larger-scale flows of gas into and out of the galactic center. Evidence for outflows on scales of many thousands of light-years, such as the large gamma-ray emitting bubbles that extend above and below the plane, suggests that energy and material injected in the central few hundred parsecs can escape along the minor axis of the galaxy and interact with the halo. On smaller scales, molecular line observations reveal expanding shells, filaments, and high-velocity features that likely trace the combined action of stellar winds, supernovae, and past activity in the central region. At the same time, bar-driven inflow continues to deliver fresh gas from the inner disk into the central molecular zone along the dust lanes, maintaining the gas reservoir over many orbital timescales. Within the bulge and central molecular zone, the overall gravitational potential is dominated by the combination of the stellar bar, the dense nuclear stellar components, and the central dark mass associated with Sagittarius A star. Gas and stars respond to this potential through a range of orbits and flows, but on the spatial scales considered in this section, the emphasis remains on the large-scale stellar distribution of the boxy bulge and on the dense, turbulent molecular gas that forms a massive, dynamically important component in the inner few hundred parsecs. On the smallest galactic scales, the central region around Sagittarius A star contains a dense stellar cluster, ionized and molecular gas flows, and the accretion structure that surrounds the central supermassive black hole. The galactic center lies at a distance of roughly 8 kiloparsecs, corresponding to about 26,000 light-years in the direction of the constellations Sagittarius Ophiuchus and Scorpius. At this distance, an angular scale of 1 arc-second corresponds to a projected distance of order 1/20th of a light-year, so observations that resolve individual stars within the central arc-second probe orbits on scales of a few thousand astronomical units from Sagittarius A star. High angular resolution infrared imaging and spectroscopy have established that the central dark mass is concentrated within a volume much smaller than this scale and has a mass of roughly 4 million times the mass of the Sun. This conclusion follows from measurements of the full three-dimensional orbits of several so-called S stars, which complete highly eccentric orbits around the dark mass, with periods ranging from about 15 to roughly 100 years. The best studied of these, often labelled with a short designation in the literature, has an orbital period of about 16 years, and a pericenter distance of only a few tens of billions of kilometres, corresponding to a few thousand times the Schwarzschild radius of a black hole with this mass. Fitting Keplerian and relativistic orbit models to decades of astrometric and spectroscopic data for these stars yields consistent values for the mass and distance of the central object, and shows that any extended mass distribution within the innermost light month must be at most a small fraction of the total. Measurements of gravitational redshift and of the precession of the stellar orbits as they pass through pericenter are consistent within current uncertainties with the predictions of general relativity for motion in the gravitational field of a compact object of this mass, further strengthening the interpretation of Sagittarius A star as a supermassive black hole rather than as a cluster of dark remnants or exotic matter. The S-star cluster occupies roughly the central light-year around Sagittarius A star, and contains dozens of stars with a range of spectral types and orbital properties. Many of the innermost stars follow eccentric, randomly oriented orbits and represent a dynamically relaxed population in the deep potential well of the black hole. Farther out within the central parsec, there are additional populations of young, massive stars arranged in one or more coherent disks or streams. These stars have ages of only a few million years and include luminous O and Wolf-Rayet stars with strong stellar winds. Their spatial distribution and orbits indicate that they may have formed in a dense gaseous disk that became gravitationally unstable and fragmented, or in infalling gas streams that collapsed while orbiting the central mass. Numerical simulations of such scenarios reproduce the observed concentration of massive stars, and their preference for high mass is often described as a top-heavy initial mass function in this environment. The combined mass of these young stars contributes non-negligibly to the gravitational potential within the central parsec, but it remains small compared with the mass of the black hole. Surrounding the stellar cluster is a complex interstellar medium consisting of ionized atomic and molecular gas phases. On scales of a few parsecs, ionized gas forms a structure often described as a three-armed or four-armed mini-spiral that orbits and flows toward the center. This ionized gas emits recombination lines in the infrared and radio and traces streams of material that are likely photoionized by the ultraviolet radiation from the young massive stars in the central parsec. Embedded within and around these ionized streams are dense molecular clumps and filaments that belong to the inner edge of the central molecular zone. Observations show that some of these molecular features follow elongated orbits that bring them close to the central cluster, where they can be tidally stretched and heated. The interaction between gas flows and the stellar cluster creates a dynamic environment in which material is continuously supplied to the vicinity of Sagittarius. A star, some of it forming stars, some of it being dispersed by stellar feedback, and some of it becoming part of the accretion flow onto the black hole. The accretion flow around Sagittarius A star is observed primarily at radio millimeter infrared and X-ray wavelengths. At radio and millimeter wavelengths, Sagittarius A star appears as a compact variable source whose size decreases with increasing frequency and approaches a scale comparable to a few times the Schwarzschild radius at millimeter wavelengths. The spectrum and variability of this emission indicate a hot magnetized plasma in which electrons emit synchrotron radiation as they spiral in magnetic fields. At infrared wavelengths, observations detect low-level continuous emission and flares that last for tens of minutes to a few hours, consistent with transient heating events or changes in the local magnetic field structure in the innermost accretion flow. X-ray observations show that Sagittarius A star is unusually faint for a supermassive black hole of its mass, with a bolometric luminosity many orders of magnitude below the Eddington limit. Most of the time, only a weak quiescent X-ray source is present, but occasional flares increase the X-ray brightness by factors of many tens. The low average luminosity and the spectral shape of the emission are well described by models of radiatively inefficient accretion flows in which most of the gravitational energy of the infalling gas is carried inward with the flow or lost in outflows rather than being radiated away. These models imply very low current accretion rates compared with the rates at which nearby stars shed mass in their winds, suggesting that only a small fraction of the available gas reaches the event horizon, while much of it is diverted into bound or unbound flows on larger scales. Recent time-resolved observations with new infrared facilities indicate that the inner flow flickers on timescales comparable to the orbital periods of matter, only a few tens of gravitational radii from the black hole, and that some fraction of the inflowing material is ejected outward, possibly contributing to weak jets or wide-angle outflows. Very long baseline interferometric observations at millimeter wavelengths by the Event Horizon Telescope have imaged the innermost emission region around Sagittarius A star, with angular resolution corresponding to a few gravitational radii. The resulting image shows a ring-like feature of emission surrounding a darker central region that is interpreted as the black hole shadow produced by the bending of light in the strong gravitational field near the event horizon. The diameter of this ring, when combined with the independently measured distance to the galactic center, agrees with the expectation for a black hole of roughly 4 million solar masses within the uncertainties of both the imaging and the stellar orbit analyses. The brightness distribution around the ring provides information about the geometry and orientation of the accretion flow and about the possible spin of the black hole. Current interpretations span models with moderate to high spin and with different magnetic field configurations, and recent analyses that use advanced imaging and machine learning techniques on existing data suggest that rapid spin may be compatible with the observations, although the exact spin magnitude and orientation remain subject of ongoing work. These high-resolution measurements, together with the stellar orbit tests, provide complementary probes of gravity in the strong field regime close to Sagittarius, a star. On somewhat larger scales, the central region shows evidence for energetic activity that affects gas and plasma out to hundreds and thousands of light-years. X-ray observations reveal chimneys and filamentary structures emerging from the central few hundred parsecs into the halo, while gamma-ray and X-ray maps show two large bubbles extending above and below the galactic plane for distances of several kiloparsecs. These so-called Fermi bubbles and associated X-ray structures are broadly symmetric about the galactic center, and point to one or more episodes in the past when energy was injected into the surrounding medium, either through enhanced star formation in the central molecular zone or through phases of higher accretion activity onto Sagittarius A star. The exact history and relative contributions of these processes are still under study, but the presence of these structures demonstrates that even though Sagittarius A star is presently in a low luminosity state, the central region has influenced the galactic halo on kiloparsec scales. Within the inner parsec, however, the dominant components remain the dense nuclear star cluster, the S-star cluster, in the immediate vicinity of the black hole, the ionized and molecular gas streams that feed and surround, the accretion flow and the compact variable source associated with Sagittarius A star itself.